Good afternoon, students. Welcome to GTQ session. The subject is communication systems, and myself, Naresh Reddy. And so I'm going to take up some good quality questions here for the subject communication systems, and I hope these questions will help you in the coming GATE examination. So let me start with the first question without wasting time. And let's make this session a kind of interactive. You can give your answers in the comment box, and I will check those answers. And so let's see. I hope you will easily can give the answers for these questions. Okay, fine. Let me start with this first question. Here, let me read it. Okay, two random variables x1 and x2 have giant PDF. This is yes. So fx1 x2 x1 comma x2 equals to is a times 2 e power minus 2 x1 plus 3 x2, where x1 and x2 both are greater than or equal 0 and 0 otherwise. Then which of the following is or true? Okay, so here, so by looking at the question, you can easily understand this is MSQ type question. So whenever you see is or are means here, so one or more options can be correct here. Okay, so this is you can understand this is MSQ type question, multiple select type question. Okay, and if you check the options, the options all about what the relation between these two random variables means, whether these two random variables are orthogonal or not, uncorrelated or not, independent or not. And of course the first option is about finding the covariance of x1 and x2. Okay, so fine. So first let's find this a value here. So we can find this a value here. How we can find a value is, so just give your answer in the comment box. So what a value will be, how to find a value, and what a value will be. Okay, yes, so this here the total area under density function equals to 1. This is integration. This is, so here x1 greater than or equal 0, so I can say x1 is equals to 0 to infinite, and x2 also 0 to infinite. So x2 and x1 both takes the values greater than or equal 0. Okay, and this is f x1 x2 x1 x2, this is, so dx1 dx2 is equals to 1. Okay, so the total area under density function equals to 1. Yes, Manish Kumar is saying the a value is 6. Okay, so let's check this. Okay, now so this is, so x1 is equals to 0 to infinite, and x2 is equals to 0 to infinite, and so a times 2 e power minus 2x1 plus 3x2, this is dx1 dx2 is equals to 1. Okay, so I'm writing a outside, this is, and you can separate x1 and x2 terms, you can separate. Okay, then it is integration x1 is equals to 0 to infinite e power minus 2x1 dx1, and integration, this is, so x2 is equals to 0 to infinite, this is e power minus 3x2 dx2 is equals to 1. Okay, so x1 and x2 terms are separable, so I'm separating them. Now this is, so if you find this integration, this is a times 2, this is e power minus 2x1 by minus 2, the limits will be 0 to infinite, and this is e power minus 3x2 by minus 3, and the limits will be 0 to infinite, equals to 1. This is. So this is a times 2. So if you substitute upper and lower limits, and it comes to be, if you substitute upper limit, that will be 0. 0 minus of minus plus, so 1 by 2. This is. And this is 0 plus 1 by 3. This will be equals to 1. So from this, you will come to know a value equals to 6. So this is how you can find a value. Okay, fine. We got a value. Now, if you see a value is 6, that's fine. And the covariance we have to find out. Okay, so the covariance of x1 and x2. So what is the formula to find covariance will be, this is expectation of x1, x2 minus expectation of x1 into x2. This is. Okay. Is equals to integration x1 is equals to 0 to infinite, x2 is equal 0 to infinite. And for which quantity you are finding expectation? The same quantity. I'm finding expectation of x1 into x2. So x1, x2 times of, okay. And what will be that given giant PDF? Okay. So fx1, x2, x1, x2, dx1, dx2. This is. Okay. Now, if you substitute the respective, x1 is equals to 0 to infinite, x2 is equal 0 to infinite. So x1, x2. So what the giant density function? So this is, we got a value 6, I'm writing 6 into e power, I'm separating that x1 and x2 terms, e power minus 2x1, e power minus 3x2, so dx1, x2, this is. Okay. Okay. Now this is 6 times 2. This is integration x1 is equals to 0 to infinite. This is. So I'm separating x1 and x2 terms. x1 into e power minus 2x1 dx1, and x2 is equals to 0 to infinite, and this is x2 into e power minus 3x2, this is dx2, this is. Okay. Now it will be equals to 6 times 2. Just do the integration of this, integration of uv. So u integration, this is, so I'm taking this is u and this is v, and integration uv, that will be, so u integration v, that is u integration v, in the limits of course this will be 0 to infinite minus integration, this is u dash. What is the differentiation of x1 with respect to x1? That is 1, and integration v, this is, it will be. Okay. Now into, and what is the value of this? Okay, I'm going to write it directly. So what the value of this we are going to get based on this, so we can write the value of this directly, we can write. So this is, okay, this quantity you will get here, okay, and it will be equals to 6 times 2. So if you substitute upper limit, that will be 0. Okay, if you substitute lower limit, okay, x1 in place of x1, if you substitute 0, that is 0 only, and minus plus here, And what is the integration? This minus minus plus here, and minus 2x1 by, so this is, yes, okay, so this is minus 4 you will get, this is, and limits will be 0 to infinite, this is, okay, and into, and this is the what you're going to get. Let me write this also. x2 is equal 0 to infinite, x2 into e power minus 3x2 dx2. Okay, yes, this is x2 is equals to 0 to infinite, x2 into e power minus 3x2 dx2, this is, and it will be, yes, 6 times 2, and if you substitute upper and lower limits, you're going to get 1 by 4 here, this is, if you substitute upper limit, that will be 0, and minus of minus plus, and if you substitute lower limit, that is 1 by 4 you will get. And similarly, if you try to do this, you are going to get, this is 1 by 9 you are going to get, this is, okay, so this is it will be 1 by 6 you are going to get here, yes, no, yes. So 1 by 6, so expectation of x1 x2 is equals to 1 by 6, you got. Yes, fine. Actually, if you're good with integration, okay, in examination don't do all these things. You can directly write, of course. So this will be equals to, okay, 1 by 2 times 2, okay, 1 by 2 square, like 1 by 4. So this is 1 by 3 square, that is 1 by 9 you will get. So 1 by 4 times 2, 1 by 9. Okay, fine. And I have to find expectation of x1 into expectation of x2, because covariance, okay, it is expectation of x1 x2 minus expectation of x1 into expectation of x2. So I have to find expectation of x1, okay, and to find expectation of x1 and expectation of x2, I'm going to find the density functions of x1 and x2. I'm going to find out, okay, and this density functions which I'm going to find out, fx1 and fx2, will be definitely useful to check whether the random variables are independent or not. Also we can check that, okay. So it's better I will find out the marginal density functions of x1 and x2. I'm going to find out, okay. So marginal density function of x1 means fx1 of x1, this is called as marginal density function of x1, or simply density function of x1, and it will be, so this is, it is fx1, fine, this is x1 x2, x1 comma x2, this is, okay. So whenever I'm finding density function of x1, you have to do integration with respect to x2, where x2 takes the values from 0 to infinite, of course, okay, and it will be integration x2 equals to 0 to infinite, okay. And what is the giant density function given? 6 times 2 e power minus 2x1 e power minus 3x2, this is dx2. So what is expectation of x1 you will get? Give your answer in the comment box, let me check. Yes. So it will be, because I'm doing integration with respect to x2, okay, x1 terms you can write outside, this is, and integration 0 to infinite e power minus 3x2 dx2, okay, and it will be equals to, this is 6 times 2 e power minus 2x1, and if you do integration of this, I'm writing this directly, this is 1 by 3, of course, okay. So the density function of x1, you will get 2 times 2 e power minus 2x1 for x1 greater than or equal 0. Similarly, you can find the density function of x2 also. This is fx2 of x2 is equals to, okay, this is I'm giving as a work, like you can do it, okay. So this is 3 times 2. How I calculated the density function of x1, similarly you can find the density function of x2 also. So it comes to be 3 times 2 e power minus 3, check this, okay, the giant density function which is given, okay, that is multiplication of this individual density functions. If you multiply these two density functions, we are getting this giant density function only we are getting. If this condition is satisfied, then we can say these two random variables, I can say, are statistically independent. So from this result we can conclude that both random variables are independent, I can say, okay. Yes, fine. And one more thing is, here itself let me write what that is, okay. So if expectation of x1 x2, okay, is equals to 0, expectation of x1 x2, you can call this as correlation function, the correlation function of x1 x2. If expectation of x1 x2 equals to 0, okay, then these two random variables are said to be orthogonal. This is, okay, okay. So if expectation of x1 x2 not equal 0, then we can't say x1 x2 orthogonal, we can't say that, okay. So here here x1, expectation of x1 x2, how much we got? 1 by 6 we got, okay. And if you see option B here, it is given that x1 x2 are orthogonal, okay, but this is incorrect, okay. As I said, if expectation of x1 x2, if that correlation function equals to 0, then only we can say x1 x2 are orthogonal. But here expectation of x1 x2 we got 1 by 6, okay, then x1 x2 are not orthogonal. So this option B, I can say, will be incorrect, okay. Next, option D, if you see, x1 x2 are statistically independent, of course, because giant density function we got multiplication of individual density functions, then I can say both are independent, of course it's true, okay. Then covariance, if you say, let me find the covariance. To find the covariance, first I will find expectation of x1. So expectation of x1, integration of x1, this is fx1, okay, x1 dx1, okay, where x1 takes the values from 0 to infinite. So for which quantity we are finding expectation x1, so the density function of x1 I am writing here, and it will be integration 0 to infinite, okay. So density function of x1, 2 you can write outside, and e power, this is minus 2x1, this is dx1, and it will be 2 times 2, okay. We already computed this integration value, we already done the value, we already got the value of this integration, okay, that is 1 by 4 you will get now. So this is 1 by 2, okay. And similarly, if you see the expectation of x2, okay, so this is integration 0 to infinite, okay, for which quantity you are finding expectation, same quantity x2, and the density function of x2, this is dx2, okay, and it will be, this is 3 times 2 x2 into e power minus 3x2 dx2, and it comes to be 3 times 2. So what is the value of this integration? Already we done in the previous of the discussion, okay. This is 1 by 9 you will get, so this is 1 by 3, okay. So expectation of x2 will be 1 by 3. Then if you see the covariance, okay, of x1 and x2, this is will be equals to, So expectation of x1, x2 we got 1 by 6 minus expectation of x1 into expectation of x2. So this will be 0. Covariance is 0. Okay. If the covariance between random variables is 0, then those two random variables are said to be uncorrelated. So I can say the given random variables x1, x2 are uncorrelated. Okay. Here, yes. And to check the random variables are independent or not, if you want to check that from the expectation point of view, if you want to check that, then it will be like this. Okay, this is if expectation of, it is something extra I am giving here, expectation of x1, x2 is equals to expectation of x1 into expectation of x2. Okay. If this condition is satisfied, but it's not only for the first order, for every possible order this equality should hold good, then I can say x1, x2 will be independent. Like it's go on. This is expectation of x1 power n, this x2 power n, this is okay, m and n can be any integers, okay, can be any positive integers. It is equals to expectation of x1 power m into expectation of x2 power n. Okay. If the equality holds good for every of these possible orders, then you can say x1, x2 will be independent. Okay. For example, if for the first order this equality holds good, but for the second order the equality is not holding good, then you can't say x1, x2 will be independent. So with reference to expectation, to check whether random variables are independent or not, for every possible order you have to see whether equality holds good or not. Okay. So what is the other easiest way to check whether random variables are independent or not is simply if the joint density function is multiplication of individual density functions, then straight away you can say both the random variables are independent. You can say it is the easiest way to check whether random variables are independent or not. Okay. Now this is one important area, so just be careful about this. Okay. Like, so it is how you can check random variables are independent or not. From joint density function you will easily come to know that if this correlation function equals to 0, then you can say random variables are orthogonal, you can say. Okay. And if the covariance equals to 0, covariance means expectation of x1, x2 minus expectation of x1 into expectation of x2. If covariance equals to 0, then you can say random variables are uncorrelated, you can say. So now let's see, so which of the options will be correct here. Yes, this is, yeah, covariance we got 0 actually, so A is incorrect. So x1, x2 are uncorrelated. Yes, x1, x2 are uncorrelated. So here options C and D will be correct. Yes, no? This is, yes, that's good. Mr. Anshuman Singh is saying if they are independent, then always uncorrelated, but vice versa is not true. Yeah, actually, the Manish Kumar and Anshuman Singh, you have to understand this. What that is, if two random variables are independent, then definitely will be uncorrelated. Okay, because if two random variables are independent, then expectation of x1, x2, yes, that will be equals to expectation of x1 into expectation of x2, you can write. If random variables are independent, then expectation of x1, x2 equals to expectation of x1 into expectation of x2, then of course this covariance will become 0. Means if two random variables are independent, then definitely will be uncorrelated, no doubt in that. But the reverse is not true, because if two random variables are, for example, uncorrelated means what? The covariance will be 0. Okay, the covariance will be 0. Then expectation of x1, x2, okay, will be equals to expectation of x1 into expectation of x2. Okay, but just by based on this result, we can't conclude that x1, x2 are independent. We can't conclude that, because as I said, not only for the first order, for every possible order, this equality should hold good. Then only you can say those two random variables are independent, you can say. So that's what. Okay, if two random variables are independent, okay, then definitely will be uncorrelated, but reverse is not always true. But the reverse is not true, I can say. Okay, yes. I hope the doubt is clear for you, Anshman Singh and Manish Kumar. Yes. Yeah, good afternoon, everyone. Yeah. Yes, Athinara and Samskriti Vishal. Good afternoon, everyone. Yeah. Let's move to the next question. Yes. Everyone read this question. I'm expecting answer from everyone this time. Okay. Yes. So the message bit sequence, this is, let me little enlarge this. Is it visible to everyone? Can you able to read it? Okay, fine. Now, yeah, the message bit sequence to a DPSK modulator. So this question is about DPSK modulation. DPSK modulator is, okay, 00101. So this is the input to a DPSK modulator. This data is differentially encoded with the unknown logic. Okay. So which logic is used to perform differential encoding? That is unknown, means that can be XOR, that can be XNOR. Okay. An unknown reference bit. Now it's tricky. Okay. So reference bit is also unknown. The carrier phase of pi is assigned to logic 0. Okay. So for bit 0, the phase shift of pi is assigned, and the phase of 0 is assigned to logic 1. Okay. For binary 1, okay, the phase of 0 is assigned. Okay. Now, yes, of course, here binary 1 represented by actual carrier. Okay. Then with respect to unmodulated carrier, the phase shift will be 0, of course, and binary 0 represented by 180 degrees phase shift of carrier minus AC cos 2 pi FCT. Then with respect to unmodulated carrier, the phase shift will be pi. Okay, fine. After encoding the data, and if the phase sequence, okay, corresponding to the first two message bits from left to right, pi and 0. Okay. So after performing differential encoding, okay, what is the phase sequence of first two message bits after encoding the phase sequence for the first two message bits given as pi and 0 respectively? Then the phases corresponding to the remaining three message bits will be, we have to find out. Okay. Yes. So Manish Kumar is saying C is the answer for this. Okay. What about others? I want to get the answers from others also. Yeah, Abhinav Datta is saying option D is correct. Okay, fine. So let's do it. So what is the message sequence given as 00101? Okay, so this is, so 0, 0, 1, 0, 1. So it is the message sequence. Mr. Unbeatable is saying option A is correct. Interesting name, Unbeatable. Fine. Okay, yeah. So I think you know how to perform differential encoding. So differential encoder output, let's see. DE output, differential encoder output. Okay. So with every differential encoder, a reference bit will be associated. Okay. A reference bit will be associated, but the reference bit is unknown. Okay. Yes. So reference bit can be 0, can be 1, but that is unknown. Okay, and what is the phase sequence I'm writing? Phase sequence. So for the first two message bits, that is given as pi and 0. Yes, no? This is pi and 0. It is a phase sequence for the first two message bits. Now, then what will be the differential encoder output? Okay, yes, the phase pi means, okay, what is the corresponding logic will be? Logic 0 or logic 1? Logic 0, no? Okay, for logic 0, the phase shift is pi, and for logic 1, the phase assigned will be 0. Okay, so after differential encoding, okay, the first two bits we are getting 0 and 1 here. Okay, so how the differential encoding will be done is, okay, this is, so this first bit 0, okay, so it is XR or XNOR with the reference bit here. Okay, so that logic is not given, so I'm writing that logic, I'm writing, okay, reference is equals to how much here? 0. This is, okay, this first bit, first message bit, this is XR or XNOR, so depending upon which logic is used. Okay, so XR or XNOR with the reference bit, then you will get the first bit of this differential encoder output you will get. Next, so this is next. From this, okay, from this we can't come to any conclusion of, so what reference bit is, what the logic used, so we can't come to know that, because the reference bit is unknown, okay, the logic also unknown. So from this result we can't come to any conclusion regarding which logic is used. We can't come to any conclusion regarding the logic used. Okay, so let me check with this. Okay, the second bit, okay, so this is, okay, so it is XR or XNOR with the previous output. This is, okay, the present message bit, okay, is XR or XNOR with the previous output. Okay, then you will get the next output you are going to get, the next bit. Okay, the present message bit is XR or XNOR with the previous output. Then you will get the next bit in the differential encoding process. So here 0, okay, that logic, okay, 0 is equals to 1. Okay, 0 logic with 0 is equals to 1 we are getting. Now from this you will come to know what is that logic is used. Now tell me, is that is XR or XNOR? Which logic is used here? XR or XNOR? XNOR, no? So this logic used, of course, is going to be, okay, XNOR. This is, yes, if you see the truth table of XNOR, okay, so 0 0 0 1 1 0 1 1, and what the output of XNOR gate will be. Okay, same input means you will get 1, different inputs means you are going to get 0. Okay, this is XNOR output. Okay, now fine, so your 0 XNOR with 0 will be 1, so what the logic used will be XNOR. Okay, so once you come to know what the logic used, okay, so then you will easily proceed with this, means you can easily complete this question. Okay, now say this. Now we will get the remaining bits in this differential encoding process. Yes, so now this is 0 1 XNOR. This is XNOR symbol now. Okay, so 1 XNOR with 1 will be 1 only. This is, now this 0, yes, so 0 XNOR with 1, okay, you are going to get 0. Okay, now yes, this, so 1 XNOR with 0, okay, 1 XNOR with 0 will be 0. Okay, Yes, we got remaining bits after differential encoding. Okay, so 1 0 0. Then what the phases we can assign? Okay, for 1 the phase will be 0, for 0 that phase will be pi. Okay, so what the phases assigned to the remaining bits will be 0 pi pi. Okay, so 0 pi pi means option C is going to be correct. Yeah, Damodar and Manish, that logic used is external. That's true. Yeah, most of you given correct answers. The option C is correct. Yes, Samskruti. Okay. So I can see most of my students here. I can with your names I can recollect like. Okay. So happy to see you all like. Okay. Abhinav Datta, Samskriti, Gautam, Suraj, yeah. Fine. So let's go to the next question. Okay. Now see this one. Yeah, let me read it for you. Okay. Yes. The normalized message signal, okay, it is denoted with MNT, M suffix NT, normalized message signal. It is having the bandwidth of 10 kilohertz. Okay. And its power content is 0.5 watts. Okay, so the power of MNT, this is, let me write here, first let me read it. Okay, and the carrier AC cos 2 pi FCT has a power content of 200 watts. If the original message signal M of t is amplitude modulated with modulation index 0.6, okay, with modulation index 0.6, then strike off this. Yes. Yeah, then you have to find the power of resultant modulated signal will be dash watts. So it is numerical answer type question, NAT type question. Okay. Yes. So you have to find the power of the resultant AM signal. So this is about amplitude modulation. This question is about amplitude modulation. Simply you have to find the power of the resultant AM signal you have to find out. Okay, so here the data regarding normalized message signal is given, okay, MNT denoted with, but the original message signal MT is amplitude modulated. Then what is the power of the resultant AM signal you have to find out. Okay, try this. Yes. Now, so what is the relation between normalized signal and the original signal? Okay, so normalized signal means, okay, this is if the given signal, okay, if you divide with what is the maximum peak of MT, okay, then the resultant signal is called as normalized signal. So this normalized signal will takes the values in between -1 and 1 only. The values possible for normalized signal will be in between -1 and 1 only. Okay, means the message signal MT is getting normalized, is divided with max of MT, so that the resultant normalized signal will takes the values between -1 and 1 only. Okay, so this is the relation between original signal and the normalized signal. Okay, fine. Now here, what the data given here is the bandwidth of MT is given, bandwidth of MNT is given, and one thing, this bandwidth of MNT and MT is going to be same only. Okay, so yes, if you divide the signal with some value here, max of MT is just some value, okay, then bandwidth of the signal is not going to be changed. So bandwidth of the original signal and normalized signal is going to be same only. Okay, and that is how much here? 10 kilohertz. Okay, and the power is 0.5 watts. Yes, the power of this normalized signal is given as 0.5 watts, and the power of this unmodulated carrier here, the power of AC cos 2 pi FCT is 200 watts. So that is AC squared by 2. Okay. The power of AC cos 2 pi FCT, AC squared by 2 R, of course, but the load resistance R is not given. Then we take the default of 1 ohm, then that is AC squared by 2. So this is given how much here? 200 watts. Yes. Okay. Now here the original message signal MT is getting amplitude modulated with the modulation index 0.6. Okay. The mu is equals to 0.6. Then you have to find the power of the resultant AM signal. We have to find out. Okay. So here, so what the message signal MT is unknown here. Okay. It is a sinusoidal message signal or non-sinusoidal message signal, that is unknown here. Okay, we don't know that. Okay, then we use the general formula, okay, to find the power of AM. So the general formula PT is equals to, this is you just see this, yeah, PT is equals to AC squared by 2 into, this is 1 plus Ka square PM, this is. Okay. Let me do it like this. If you see the AM expression, let me write in this way. What is the general expression of AM will be, that is AC times 2 1 plus Ka MT cos 2 pi FCT. It is a general expression of AM signal. Yeah, good. Okay. Suraj, Anshuman and Namrata and Abhinav Datta is saying that is 236 watts. Yes. I think that's the correct answer. Yes. So here, now I'm going to write this in terms of MNT. I'm going to write, okay, because the data related to normalized message signal is given. The power of MNT, okay, is given here. So I'm going to write in terms of MNT. So this will be AC times 2 1 plus, okay, Ka, okay, MT. What you can write? This is MNT into maximum peak of MT. This is maximum peak of MT into MNT. This is cos 2 pi FCT. Okay, then it will be AC times 2 1 plus Ka into maximum peak of MT is nothing but mu only. This is the general formula to find mu. The Ka into maximum peak of MT will be equals to mu. So this is mu into MNT cos 2 pi FCT. Okay. So in terms of normalized message signal, the expression of AM signal will be like this. Then what is the power of this AM signal? Okay. So the first term will be AC cos 2 pi FCT. The power will be AC squared by 2 plus. Okay. The second term will be AC mu MNT cos 2 pi FCT. Okay. So what that power will be equals to? Okay. So this AC is AC squared only. Mu means mu square. The power of MNT. The power of MNT I'm denoting with PMN. Okay. The power of cos 2 pi FCT is 1 by 2. Okay. The second term. Okay. The power of the second term is going to be like this. Okay. Then if you take, let me rewrite like this. So if you take AC squared by 2 common, this is 1 plus mu square into power of the normalized message signal. And if you substitute here, AC squared by 2 is 200, okay, 1 plus mu is given how much here is 0.6 square into the power of normalized message signal is 0.5. Okay, so do check with the calcium. Yes, let me check with calcium. Yes, this is 0.6 square to 0.5. Yeah, this is 236. 236 watts. Okay. Yes, in the numerical answer type questions, so do check for the units. Okay, in which units is expecting answer. He is expecting in watts. Okay, how much that is? 236. So 236 will be the correct answer. So I'm impressed. Most of you given correct answers. Very good. Yeah. Next question. Let's proceed to next question. Yes. See this here. Let me read it for you. Okay. So this is about DSB-SC modulation. A DSB-SC signal is generated by multiplying MT with the periodic rectangular waveform, okay, shown below. Okay, this is the periodic rectangular waveform, that is PT. Okay, I think you can see it. So here DSB-SC signal is generated by multiplying MT with this PT. Okay, and filtering the product with a band pass filter. Okay, tuned to 1 by Tp. The band pass filter is tuned to 1 by Tp, means the pass band of band pass filter is centered about 1 by Tp, you have to understand. And with a bandwidth of 2 omega, this is 2 omega. Okay, so if you see the band pass filter now, let me, okay, the band pass filter, if you see, the transfer function of a band pass filter the default we take as ideal filter only. Okay, and this is tuned to 1 by Tp, so it is centered about 1 by Tp and having the bandwidth of 2 omega. Okay, it is having the bandwidth of 2 omega. Fine, where omega is the message bandwidth. Okay, where omega is the message bandwidth. So let me take the message spectrum like this. The default message spectrum you can take like this. MF. Okay, message bandwidth is omega. This is. So omega hertz, you can understand the message bandwidth is. Okay, now, so because this is given normal frequency only, this 1 by Tp is equals Fc is given, this is normal frequency. So here the data is given in terms of normal frequencies only. Okay, so this is, so message signal having bandwidth of omega hertz, you can understand with respect to F. Now the resultant DSB-SC signal is, okay, the resultant DSB-SC signal is AC dash MT sine 2 pi FCT. Okay, this is, okay, ignore this. Okay, the expression for the resultant DSB-SC signal is AC dash MT sine 2 pi FCT, where Fc equals to 1 by Tp. Okay, then what this AC dash value will be? What the value of AC dash? It is MCQ type question, so one of the given options will be correct here. Okay. Now what is Tp here? You can understand the Tp is the period. Okay, okay, what is the period of this okay, periodic waveform PT? Okay, that period will be Tp here. This is, okay, yes. So Pramit Banerjee asking one question: how many marks we can expect from analog communication? Okay, so Pramit, what is the current trend is from the from the last few years. Okay, they are giving most of the weightage to digital communication only. Okay, the weightage to analog communication, okay, drastically reduced nowadays. So most of the weightage they are giving to digital communication. So from analog communication you can expect some 2 to 4 marks you can expect. Okay, it's what my prediction is. Okay, digital communication, most of the questions they're giving in the last couple of years, this is what happening. So in the coming GATE examination they can change the trend, okay, because this is something unexpected. Okay, so we can't expect like the weightage exactly, we can't distribute weightage just like that. Okay, so it's a kind of random and dynamic. So the trend they can change, they can give most in the coming GATE. Okay, we don't know, okay, how they will distribute the weightage between analog and digital. Okay, but generally we expect, okay, the most of the weightage will be for digital, we can expect. Okay, yes, fine. So Amit is saying C and Suraj is saying D. Okay, yeah, let's see. So here, yeah, the DSB-SC signal is how it is got just multiplying MT with PT. Okay, just by multiplying MT with PT, okay, the periodic waveform, they are getting DSB-SC signal. So the DSB-SC, this filtered signal, okay, this multiplied signal, this product, okay, this product is passed through this band pass filter. Okay, the band pass filter allows only these band of frequencies. So 1 by TP is FC na, so the band pass filter, I can say it is centered at FC, I can say this is. Okay, okay, bandwidth of 2 omega means it is allowing from FC minus omega to FC plus omega, you can understand. So the band pass filter is centered at FC with bandwidth of 2 omega. So the band pass filter is allowing only these band of frequencies. Okay, so to do that filtering, okay, present in periodic signal, we can take the help of Fourier series. Okay, so I'm going to write the Fourier series representation of this periodic signal PT. Okay, so the Fourier series representation of PT is equals to, okay, let me write trigonometric Fourier series representation. Okay, because the DSB-SC term I'm expecting in terms of sine here, I'm expecting in terms of sine and cos. So let me write the trigonometric Fourier series representation of PT. Okay, so that is A naught plus summation n equals to 1 to infinite A n cos n omega naughting plus B n sine n omega naughting, this is. Okay, so A naught simply will give you the DC value of the given periodic signal. So what is the DC value of this will be 0, A naught will be 0. And this P of t which is given here, it is an odd signal. Okay, so for odd signal के लिए, for odd signal A n will be 0, for even signal B n will be 0. Okay, but this is odd signal A n will be 0. Then what will be the Fourier series representation? PT is equals to, this is summation n equals to 1 to infinite. So B n, this is sine n omega naught t. Okay, so let me find out Bn, the TFS coefficient Bn. Okay, how to find Bn? It is equals to 2 by t integration 0 to t, this is Pt sine n omega naught t, this is omega naught, yeah, dt, this is. So it is how you can find this Pt, how you can find Bn. Okay, so find this Bn and yeah, Suraj and Barik saying option D is correct, and Amit is saying option C is correct. Yes. Yes, fine. Okay, so T here is the period. So what is the period here? TP only, no? So in place of T you can substitute TP here. This is okay, and this omega naught. Omega naught is equals to 2 pi f naught. This is okay. And f naught equals, of course, 1 by Tp. This is f naught is the fundamental frequency, that is f naught is equals 1 by Tp. Yes. Yeah, let me write like this. This is, and it is 0 to Tp by 2. This is, so from 0 to Tp by 2 this Pt is 1, and from Tp by 2 to Tp the Pt is minus 1. So let me substitute here. This is, so this will be 2 by Tp. This is, and integration 0 to Tp by 2 the Pt is 1. This is sine n omega naught t dt plus, and Tp by 2 Tp, this is Pt is minus 1. So this is minus sine n omega naught t dt. This is okay. Yes, if you do this integration, this is 2 by Tp, and integration of sine will be minus cos. So this is minus cos n omega naught t by n omega naught. This is 0 to Tp by 2. This is, an integration of minus sign will be cos. This is cos n omega naught t by n omega naught. This is, so Tp by 2 to Tp. This is okay, and it will be, so 2 by, this is n omega naught Tp. This is n omega naught I am writing outside, and if you substitute the limits here, if you substitute upper limits, n omega naught Tp by 2, this is minus, okay, so n omega naught Tp by 2. So this is, if you see, this is 2 pi f naught is equals to 1 by Tp. Okay, then if you see omega naught Tp, okay, if you multiply this with Tp, this is 2 pi, okay, and omega naught Tp by 2, okay, so this omega naught Tp by 2 will be pi, you will get, this is okay. So omega naught Tp is 2 pi, omega naught Tp by 2 will be pi, and if you substitute now, this is okay, n, this is cos, this is okay, omega naught Tp by 2, omega naught Tp by 2 will be pi, so this is cos n pi. This is, so minus of minus will be plus, cos 0 will be 1. This is plus, and if you substitute upper limit here, okay, cos n omega naught Tp, omega naught Tp will be 2 pi. This is cos 2n pi minus this n omega naught Tp by 2, omega naught Tp by 2 will be pi. This is cos n pi. This is okay. Yeah, so this cos 2 n pi, so cos 2 n pi will be equals to 1. So n can be any integer, you can take cos 2 n pi will be 1, and cos n pi will be minus 1 power n. Okay, so this cos n pi, this is minus 1 power n, and this will be, this is omega naught Tp will be 2 pi na. So if you substitute that, this is 1 by n pi, you will get this is, okay, so this 1 plus 1 will be 2, okay, and minus, okay, so minus 1 power n and minus of minus 1 power n, so this is minus 2 times 2 minus 1 power n, this is, so this will be, you can write this as 2 by n pi if you take common, this is, here 2 by n pi, this is 1 minus 1 power n, this is, okay. Now so this bn I can write, it is equals to 0 if n even, okay, if n is even, minus 1 power n will be 1 only, so 1 minus 1 will be 0, and if n odd, so minus 1 power n is minus 1, so okay, minus minus will become plus, so it is 4 by n pi, this is, so if n is odd, this is, so bn will be equals to, then yes, so st is equals to mt into pt, okay, and what about this pt? Pt is what? Summation n is equals to 1 to infinite, this is bn sine n omega naught t, this is, omega naught means this is 2 pi f naught t, this is, okay. Now if you substitute, then st will be equals to, this is mt, so bn we got 4 by n pi if n is odd, okay, and it is 0 when n is even, okay. So if n is equals 1, okay, n equals 1, this is 4 by pi, okay, n equals to 1, this is sine 2 pi f naught t, okay, and if n equals to 3 here, okay, n equals 3, this is 4 by 3 pi, okay, sine, so this is 2 pi 3 f naught t, and plus it's go on. Now this is given to a band pass filter, okay, then what will be the band pass filter output? The band pass filter output is going to be DSB-SC signal, okay, and it is clearly given that the filter, okay, if you recall the filter characteristics, it is centered at Fc, okay, Fc means 1 by Tp of course, and bandwidth of 2 omega, this is, it is allowing from Fc minus omega to Fc plus omega, okay, and here this f naught is also equals to 1 by Tp only, that is, okay, the fundamental frequency of the given periodic waveform, okay, f naught is 1 by Tp of course. So if you see the first term, which frequency is present in this first term, okay, if you multiply mt with sine 2 pi f naught t, so which frequency is present in this term is, okay, the message spectrum will be shifted to right by f naught, okay, the message spectrum, okay, the message bandwidth is omega na, then this is message spectrum is going to be like this, message spectrum mf, Which frequency is present in mt sine 2 pi f naught? The message spectrum shifted to right by f naught. Okay, right by 1 by Tp. Okay, the message spectrum shifted to right by f naught. Then f naught minus omega to f naught plus omega. Okay, where f naught equals 1 by Tp, of course. Okay, so this first term is, of course, is allowed by this bandpass filter. So if you see which frequency is present in this, okay, the message spectrum shifted to right by f naught. Okay, where f naught equals to same as fc only. Okay, f naught equals 1 by Tp, fc also 1 by Tp. Okay, so the message spectrum is shifted to right by fc. So fc minus omega to fc plus omega. So only this first term is allowed by the filter. The second term, the subsequent terms are not allowed by the filter. The message spectrum shifted to right by 3f naught. Okay, 3f naught means 3 by Tp, and that is not allowed by the filter. Only this first term will be allowed. So this will be, so 4 by pi mt sine 2 pi f naught t. It is a filter output. So what is the DSB-SC signal given in the question? So that is given as AC dash mt sine 2 pi fct, no? Okay, AC dash mt sine 2 pi fct, where fc is 1 by Tp. Okay, so this is, so it will be, the given DSB-SC signal is AC dash mt sine 2 pi fct. Okay, where fc, of course, is given as 1 by Tp, and f naught is also 1 by Tp. So from comparison, AC dash will be equals to 4 by pi. Okay, yes, AC dash is 4 by pi. This is, so option D is going to be correct. Option D will be correct. So let's proceed to the next question. So let me read it and you just try this. Okay, the transmitted power of an AM wave with 100% tone modulation and peak envelope power 32 kilowatt is dash kilowatt. Okay, so try this question. Yes. Yeah, thank you, Deepshika. Thanks for that. Okay. Yeah, nice to see you too. Fine. Yes. Yes, here it is also, it is about amplitude modulation, okay, with 100% tone modulation. Tone modulation means here message signal having single frequency, what you can understand. So it is single tone modulation. Simply tone modulation means single tone modulation, means message signal having single frequency. Message signal having single frequency means here the message signal is a sinusoidal message signal, you can understand. Okay, fine. So this is about single tone AM. This is single tone AM, message signal having single frequency. And mu is given how much here? Mu is equals to 1 given. Okay. So you have to find transmitted power of AM. So the power of AM signal you have to find out. Okay. And the peak envelope power is given 32 kilowatt. Okay. So the power of peak envelope. Okay. What is the peak envelope of AM signal? If you see AM signal, okay, this is. So this is actually the envelope here. This is, okay. The peak envelope means this is, yeah. So peak envelope means this, the peak of the envelope. So this is of course A max. So peak envelope here, okay, is nothing but A max, the peak of the envelope. Okay, so what is the peak of the envelope is A max here. Okay, the power of that A max is given as 32 kilowatt. Okay, so this is, yeah, A max, we know that is AC into 1 plus mu. For singleton AM, A max is AC into 1 plus mu. Okay, and the power of this peak envelope power, okay, the peak envelope power is equal to, this is simply A max square. It is just some DC quantity A max, okay, just some value, just squaring will give its power. Okay, that is A max square. So that is AC into 1 plus mu, this is whole square, is equals to, this is 32 kilowatt. Okay, this is, and here mu is given 1. If you substitute mu 1 here, this is, so this is AC times 2, this is, so 2 square is 4, this is 32 kilowatt. Then AC square is how much here? Let me find AC square, that is 8 kilowatt. Okay, then the AM power we have to find out, that is, so PC into 1 plus mu squared by 2, this is, so PT is PC into 1 plus mu squared by 2. Yes, so AC squared by 2 will be, this is 4 kilowatt into 1 plus mu is given as 1, so it comes to be 6 kilowatt. Okay, yes, so here the AM power is expected in kilowatts only, is expecting in kilowatts only, so that is 6 kilowatts will be the answer. Okay. Yeah, Adarsh Garg, Suraj, Manish Kumar, Abhinav Datta, Barik, correct answers. Yes, let's proceed to the next question. Now, so I'm curious that I want to see how many of you will give you the correct answer for this. Yes, the input to a filter with impulse response ht and transfer function hf, okay, is a white noise process with power spectral density n0 by 2. Okay, the power spectral density is denoted with Sx of f here. Okay, so here a filter is given here, okay, whose impulse response is ht and transfer function is hf, of course. Yes, here the input to this filter is a white noise process. That white noise process I'm denoting with xt, okay, and the power spectral density of this is given as n0 by 2. The power spectral density of this xt is n0 by 2. Okay, then the cross correlation function Rxy tau will be, so here the output of the filter is yt, you can understand. Okay, now the cross correlation function Rxy tau we have to find out. Rx by tau. Yeah, Anshuman Singh is saying option C is correct. I want to see answers from others. This is easy question. Yes. Let me do this. So this cross correlation function Rx by tau is equals to, this is Rx tau convolve with, this is H tau. This is the relation. It's a very well known relation for you. So we already derived this in the classroom. Okay. Now, Rx tau is the autocorrelation function of the input. So this is Rx tau is equals to, how to get autocorrelation function from power spectral density, that is inverse Fourier transformation of power spectral density will give you autocorrelation function. Yes, no? The autocorrelation function and power spectral density both are Fourier transform pairs. Okay. Now this is inverse Fourier transformation of n0 by 2. This is. So this Rx tau will be equals to, this is n0 by 2 del tau. This is the inverse Fourier transformation of 1 will be del tau. This is. Okay. Now this Rxy tau is equals to this Rx tau convolution with H tau. This is. So n0 by 2 is just some constant you can write outside. n0 by 2 del tau convolve with H tau will be equals to H of tau only. So if you do convolution of impulse function with any function, any other function, okay, so then xt convolve with delta will be xt only you will get. Okay, so that is H of tau you will get. So which option is correct here? n0 by 2 H tau. So this option C will be correct, no? Yes. Option C will be correct. Yeah, Abid Bashir. Okay, yes, C will be correct. I'm very happy, like, yes. Yeah, Divyanshi, option C is correct. Fine. I'm happy with your answers because so most of you giving correct answers. Fine. So let's proceed to the next question. Yeah, this is a typical question. Okay. Yeah, let's do it. Can you see it? Let me elaborate it little bit. Yes. Now let me read it for you. So consider a random process with sample function xt is equals to a cos 2 pi f naught t plus theta. Where a and f naught are constants. So a and f naught are constants and theta is a random variable with the PDF. Okay, so f theta of theta is 1 by 2 pi where mod theta less than or equals to pi. Means here theta takes the values from minus pi to pi. Then which of the following is or are true? So whenever you see a phrasing like this, then you can understand this is MSQ type question. So here one or more options can be correct. So this is MSQ type question. Okay. And these options are about finding ensemble averages and time averages. Okay. Ensemble mean is time average mean, ensemble mean square value is time average mean square value, and ACF, and option D is it is a ergodic random process. When you can say a random process is ergodic random process, if ensemble averages, if all possible ensemble averages equals to time averages, then you can say that is ergodic random process. Okay. So let's find this. Yeah. Let me find ensemble average mean first. Yeah. So ensemble average mean you can denote with expectation of xt. Okay. This is xt bar, and it will be the integration. Okay. For which quantity you are finding expectation? The same quantity x of t. Okay, multiplied with the density function. So what is the random variable associated here? Theta is the random variable associated. Then this is f of theta d theta, where theta takes the values from minus pi to pi. Tell me, what is the ensemble mean you are getting? This is ensemble mean I am finding. Ensemble mean. What you are getting? Post your answers in the chat box. What is the ensemble mean you are getting? I want to see that. Suraj is saying the mean is 0. Yes, let's find this. So it will be, so integration minus pi to pi xt. Xt is equals to, this is a cos 2 pi f naught t plus theta. F of theta is how much here? 1 by 2 pi. This is at d theta. Okay. Now it will be a by 2 pi. Okay. Integration of cos will be sine. This is sine 2 pi f naught t plus theta divided by, okay, differentiation of this quantity with respect to theta, that is 1 only. The limits will be minus pi to pi. Okay. Then it will be a by 2 pi. If you substitute the limits, what you will get here, this is sine 2 pi f naught t plus pi. This is minus sine 2 pi f naught t minus pi. This is okay. So it is, you can write this as a by 2 pi. This is in the form of sine a plus b minus sine a minus b. 2 cos a sine b this is. So this is 2 cos a sine b sine pi. This is sine a plus b minus sine a minus b. 2 cos a sine b. Sine pi will be 0. So this is 0 you will get. So ensemble mean we are getting 0. Okay. Yeah, mean 0. Now, so if you see ensemble mean square value, let me find, this is expectation of x square t. Okay, so this is, it is ensemble mean square value, it is integration x square t, this is multiplied with the density function, that is f of theta d theta minus pi to pi, and it will be minus pi to pi. So this is xt is given as, so it is a square, xt given as a cos 2 pi f naught t plus theta, and if you square it, so this is fine, cos square, okay, into f of theta will be 1 by 2 pi d theta. Yes, if you do this, a square by 2 pi you can get outside. Okay, cos square theta 1 plus cos 2 theta by 2, this is minus pi to pi, this is 1 plus cos 4 pi f naught t plus 2 theta by 2, this is okay. Now, so this is, yeah, so a square by 2 pi means 4 pi, this is, and what about the first term 1, integration will be theta, and if you substitute the limits you get 2 pi, pi plus pi will be 2 pi, and what about the second term, this is, so integration, I'm directly writing here, integration of cos will be sine, you will get, this is sine 4 pi f naught t plus 2 theta by differentiation of this with respect to theta, that is 2 minus pi to pi, this is, so here you have to substitute limits here in this quantity, upper and lower limits. Okay, then it is so you will get sine 4 pi f naught t plus 2 pi minus of sine 4 pi f naught t plus 2 pi minus of sine 4 pi f naught t minus 2 pi. Okay, same like previous. Okay, you will get that will be equals to cos 4 pi f naught t into sine 2 pi, you will get same like previous. Okay, this is cos 4 pi f naught t into sine 2 pi, you will get sine 2 pi will be 0. Okay, so this second term, this quantity, of course you will get 0, just like the previous, this will be 0. Then this is expectation of x square t, so this will be a square by 2, you will get. Okay, the mean square value I'm getting 1 by 2. Yes, Abdul Kumar, we do questions on information theory and noise also. Of course we will do. Okay, now ACF, if you see, this is so this is ensemble ACF. This is, so this is expectation of xt into xt plus tau. This is, yes, it will be expectation of xt. xt is a cos 2 pi f naught t plus theta into xt plus tau, this is 2 pi f naught t plus 2 pi f naught tau plus theta, this is, okay. Now this is cos A cos B cos A plus B plus cos A minus B by 2. So you can write A square by 2 outside, and if you apply expectation to each of the terms, this is cos A plus B, this is, so this is A plus B means this is 4 pi f naught t plus 2 pi f naught tau plus 2 theta cos A plus B plus cos A minus B by 2, A squared by 2 into expectation of cos A minus B, you will get cos 2 pi f naught tau, okay. I'm writing directly, okay. If you find the expectation of this, okay, same like previous, okay, if you see expectation of this, you will get 0, okay. So this is cosine is function of theta, okay, and theta is uniformly distributed from minus pi to pi. Then if you find expectation of this, you will get 0, and here no theta terms here, okay. Then you can see this is a deterministic signal. Expectation of deterministic signal will be same signal only, so you will get here, so this will be A square by 2, this is cos 2 pi f naught tau. It is an ensemble ACF we got. So we got so Manish Kumar, ensemble mean means the normal mean only, like what we calculated, okay. So simply that expectation of xt, that's it. This is ensemble mean, expectation of xt. So if you see the definition of this actually, so the statistical averages we find at a specific time instant by considering all possible sample functions over all possible sample functions will be called as ensemble averages, okay. So we find ensemble averages at a specific time instant by considering all possible sample functions, that is called as ensemble averages. The time averages we find for the given sample function over a specific time interval, okay, for the given sample function over a specific time interval, those averages will be called as time averages, okay. Now let's find the time averages here. The time averages will be interesting, yes. Yeah, time averages will be little tricky, okay, and let me confirm this, what is that is, till now in GATE examination they never given questions like finding time averages, okay. So the chance is there, okay, in the coming examination, okay. So take care of this, how to find time averages, yes. So if you see time average mean, okay, this is, we denote like this, some special brackets like this, it is the time average mean, okay. The formula will be, what is the mathematical formula to be used is, yes, limit t tends to infinite 1 by 2t, this is integration minus t to t, this is xt dt. It is simply finding the average of xt, okay, in the time interval minus t to t, that's it. So remember this formula, okay, will be useful to you in the examination, okay. It is simply finding the average only, just finding the average of xt in the time interval minus t to t, okay. So in finding time averages, the density functions are not involved, you have to understand that, okay, fine. Now let me find this. So this is limit t tends to infinite 1 by 2t integration minus t to t. So xt is equals to, this is a cos 2 pi f naught t plus theta d theta. Okay, now so it will be, it is dt actually, so be careful about this. Your density function is not involved. Okay, so here the integration is not with respect to theta. You should be careful about this. It is simply finding the average of xt in the time interval minus t to t. Your integration is with respect to t, you have to understand. Okay, so Barak, you are saying A, B, C are correct. Yes, if A, B, C are correct, then D of course will become correct, no? Okay, because if all statistical averages are same, then that becomes of course ergodic random process. Means if ensemble averages equals to time averages, then will become ergodic. So if A, B, C are correct, then eventually D also will become correct. Okay, fine. So limit t tends to infinite, this is 1 by 2t. Yes, so it is a by 2t. I am writing integration of cos will be sine, this is sine 2 pi f naught t plus theta by, this is, what is the differentiation of this with respect to theta? Differentiation of this quantity with respect to t. Differentiation of this quantity with respect to t, that is 2 pi f naught. Okay, so limits will be, of course, this is minus t to t. This is okay. Yes. So do check what you will get for that. Just let me write here. So I'm doing here itself. Say this. This is, I'm continuing here. Limit t tends to infinite 1 by 2t. Okay, and into 2 pi f naught. You can write 2 pi f naught outside. Okay, and if you substitute the limits here, so this is sine 2 pi f naught. You have to substitute limits in place of t. The integration is with respect to t, na? So in place of small t, you have to substitute the limits. So this is, so 2 pi f naught t plus theta. Okay, and minus, this is sine, if you substitute lower limits, minus t plus theta plus t, yeah, plus theta, fine. Substitute upper and lower limits. Okay, and f naught equals to 1 by t. The fundamental frequency f naught equals to 1 by t. Then f naught t is equals to 1. Yes, this will be limit t tends to infinite. This is, so this is, it is 4 pi f naught t will be 1. This is, yeah. So this is sine, so this is f naught t is equals to 1. Sine 2 pi plus theta minus sine minus 2 pi plus theta. Okay, then you can write this as this quantity, if you see. So this is sine 2 pi plus theta. So this is, so this is plus sine 2 pi minus theta, you can write. Sine minus x is minus sine x. So this is sine a plus b plus sine a minus b. Okay, 2 sine a cos b. This is 2 sine a cos b. This is sine a plus b plus sine a minus b, 2 sine a cos b, and sine 2 pi will be 0. So this will be 0, and total quantity will become 0. So this, so time average mean you will get 0. Same like you will find that other time averages you can find. I'm continuing here. This is, yes, time average mean square value. Okay, this is, it will be equals to, this is limit t tends to infinite 1 by 2t integration minus t to t x squared t dt. This is okay. So try this. Limit t tends to infinite 1 by 2t integration minus t to t. This is a square cos square 2 pi f naught t plus theta, and this is dt. So if you do in the cos square theta, you can add 1 plus cos 2 theta by 2. This is 1 plus cos 2 theta by 2. This is cos square t1 plus cos 2 theta by 2, cos square theta. So let me write it directly. So this is limit t tends to infinite. This is a square by 2t. Okay, so a square by 2 I'm writing outside. Okay, then it is a square by 4t you will get. Okay, so a square by 2 I'm writing outside. So 1 by 2t times 2, a square by 2, a square by 4t. The first term will be constant. Okay, the integration of this 1 will be t only, and after substituting limits 2t you will get, plus. What about second term? Okay, the integration of cos will be sine. Okay, then after substituting limits, upper and lower limits, in place of integration of cos you will get sine, same like previous. Okay, then after that substitute the limits. Okay, so after, and then variance also is going to be same, ensemble average variance and time average variance is also going to be same. If all these quantities are equal, then of course it is going to be ergodic random process. So here, yes, fine. Yeah, Anshuman Singh. So here mean same, mean square value same, and ACF also we got same. Okay, then variance also we get same. So if all the statistical averages are equal, then yes, you can call that as ergodic random process. That is going to be ergodic random process. So here A, B, C, D will be correct. So in examination point of view, okay, whenever you're checking whether this is ergodic random process or not, okay, just see whether this mean square value ACF is same or not. Okay, if at all same, then yes, straight away you can say that is ergodic random process, you can say. Okay, fine. Let's see the next question. Yeah, try this question. Yeah, thanks Adarsh Kumar, thanks for that. Yes, the message signal of 4 cos 2 pi times 2 10t is given to both frequency and phase modulators. Fine. And given that FC is equals 1000 Hz, the carrier frequency. So I'm taking questions in random sequence. I'm not taking the questions in topic wise. I'm not taking, because in actual GATE examination also you don't expect questions topic wise. Okay, first amplitude modulation, next angle modulation, next PCM, DPCM. We don't get questions in sequence. I'm taking the questions in the similar way. So I'm not taking in a standard sequence. I'm taking randomly the questions. Okay, and KF is given as 12.5 Hertz per volt. Okay, the frequency sensitivity of FM modulator KF is given. What must be KP? KP means the phase sensitivity of phase modulator. So what must be KP of phase modulator to get modulation index same as FM? Okay, yes. So to get modulation index of PM same as modulation index of FM, okay, what must be KP value? We have to find out. What must be KP value? So everyone try this question. It's easy. Try this question. Of PM you can write KPAM, you can write, and beta of FM directly this is KFAM by FM. It will be this is, then AM will be cancelled. Then KP will be equals to this is KF by AM. This is so this is KF is equals to how much here? 12.5 by this is AM is equals to how much? Message signal amplitude is message signal KF by FM. No, this is yes. This is message frequency is what here? 10. So this is 1.25 you will get. KP will be equals to. So 1.25, so option A will be correct here. So 1.25. Yes, fine. Let's proceed to the next question. So actually just take this as, because it is given radians per volt, so kF units take here as radians per second volt. So if you take the radians per second volt, so you can write the units of kp. It is also one possible unit of kp. Okay, radians per second volt. Take that as radians per second volt. Okay. So kf by fm. So fm is hertz. Hertz means per second. You can write per second cancel. You get radians per volt. You will get. Okay, fine. 1.25 will be the answer for this. So if you see the next question, this is interesting. Question number 9. I want to see how many of you can give the answer for this. Yes. Yes, this is for n comma k. Yeah, for n comma k Hamming code. Okay, the code rate with number of parity bits n minus k equals to 4. We have to find out. Yeah, Anshman Singh is saying 11 by 15. So let's check this. Okay, so we have to find the code rate. The code rate is actually equals to, this is, code rate is k by n. Okay, for n comma k block code or Hamming code here, the code rate, the formula is k by n. So here number of, here Hamming code it is given. So what is Hamming code? A single error correcting perfect code, okay, will be called as Hamming code. Okay, yes, so for Hamming code, so if you see Hamming bound equals to, okay, 2 power n minus k. Okay, it is Hamming bound actually. Hamming bound is equal to 2 power n minus k greater than or equals to summation I is equals to 0 to t nci. Okay, nci. This is Hamming bound. Okay, so it is t is number of errors it can correct. Okay, till how many errors the LBC can correct, that is t here. So n minus k is number of parity bits. Okay, so according to Hamming bound, you have to select parity bits such that this condition is satisfied. Then only your LBC can comfortably correct up to t errors. And this is, so n minus k I'm denoting with m here. So 2 power m is equals to n plus 1. So number of parity bits n minus k I'm denoting with m. So for Hamming code, so n is equals to 2 power m minus 1. Okay, n is equals to 2 power m minus 1. And what about k? So k is equals to actually n minus m. M is total number of bits in a code word and m is number of parity bits. So from total number of bits, if you subtract parity bits, you will get the number of message bits. Okay, so n minus m. So n is what? 2 power m minus 1. N is equals to minus m. So for Hamming code, the code rate will be equals to k by n. K is equals to 2 power m minus m minus 1 by, okay, and n is equals to 2 power m minus 1. Okay, and number of parity bits n minus k, that is m, is given 4 given in the question. And if you substitute here, this is, in place of m substitute 4. Okay, so 16 minus 5, this is 11. Okay, and 16 minus 1, this is 11 by 15. So try with calculating. what is this 11 by 15 will be equals to? Yes, .733, okay, will be the answer. So this is, so what is the answer here is 0.733 will be the answer. Let's move to the next question. Yeah, so this is information theory. This is related to, yes, two binary symmetric channels shown below are connected in cascade. So this is here, you can say this is channel 1 and this is channel 2. So let me enlarge this little bit. Okay, so two binary symmetric channels are connected in cascade. Okay, these two binary symmetric channels are connected in cascade, channel 1 and channel 2. Okay, so here, so for binary symmetric channel, okay, P0 by 1 equals to P1 by 0. Okay, so if you see, binary means 0 1 transmitted and 0 1 received, like this. 0 1 transmitted and 0 1 will be received. So for binary symmetric channel, the probability of 0 received as 1 is same as transmitted 1 received as 0. Okay, so P1 by 0 equals to P0 by 1. So this is, okay, so P1 by 0 is equals to P0 by 1. You can see 0.1, 0.1. Here also 0.25, 0.25. So two binary symmetric channels are connected in cascade. Okay, and the equivalent channel is this. Okay, x1, x2 inputs and z1, z2 will be the outputs. Okay, so what is the output of the first channel? Okay, the same will be given as the input to second channel. This y1, y2 is given as the input to second channel. Okay, and this is the equivalent channel. Okay, and the corresponding transition probabilities, the channel probabilities denoted like this: P11, P12, okay, P21, P22, like this, denoted like this. Okay, and the capacity of the first channel is denoted with C1 here. So what is the capacity of the second binary symmetric channel? What is the channel? Simply capacity means channel capacity. What is the channel capacity of, so first binary symmetric system is C1. The capacity of the second one is C2, and the capacity of this equivalent channel is C. Then which of the following is or are true? Okay, so whenever you see a phrasing like this, so this is MSQ type question, you can understand, multiple select type question. So one or more options can be correct. Okay, so it is MSQ type question. So here this is just comparing the channel capacities here. Okay, the relation between C1, C2 and C. So which of the following will be true? So first we have to find the capacity of each of these channels, we have to find out. Okay, yes. So if you see, so for binary symmetric channel, I think you know this. This is, if you see x1, x2, y1, y2, this is. I'm taking one binary symmetric channel like this. X1, x2 inputs and y1, y2 are the outputs. Okay. So this is for binary symmetric channel, this P1 by 0 and P0 by 1 will be same. So this is P and P. Okay. And this P0 by 0, this is, I'm denoting with Q, and this is Q, I'm denoting with, where Q is of course 1 minus P. So for binary symmetric channel, you can understand this is 0 1 transmitted and 0 1 received. Okay, so 0 to be received as 1, transmitted 0 to be received as 1, probability if at all P, then transmitted 0 to be received as 0, that is 1 minus P, that is I'm denoting with Q. Okay, and for this binary symmetric channel, the capacity of the binary symmetric channel, this is. Okay, so this is the first one. Okay, So this is for the first binary symmetric channel, the inputs are x1, x2, outputs are y1, y2, and for a binary symmetric channel, the capacity will be 1 plus p log p base. Try to give the answer for this. Yes. Yes, it will be 1 plus. So here this is p is 0.1 and q is 0.9. So this is 0.1 log 0.1 base 2. So take care of here. The base is going to be 2 only here. Okay. Plus 0.9 log 0.9 base 2. So if you try this, okay, try with calcium. So what you're going to get for this is 0.531 bits per, this is symbol. The channel capacity is actually how you will get this formula is this is maximum of mutual information. Okay, will give you the channel capacity. Okay, and what the units of mutual information is bits per symbol, and the units of channel capacity also bits per symbol only. So 0.531 bits per symbol you will get. Okay, yes. Next, similarly, the capacity of the second channel here. What is the capacity of the second channel? For the second binary symmetric channel, P will be 0.25 and Q is 0.75. So this is 1 plus 0.25. This is log 0.25 base 2 plus 0.75 log 0.75 base 2. So if you do this, you will come to know this is 0.1887 you will get. This is, do check this. Okay, so I don't want to waste your time, I'm writing directly. This is what you will get, C2. So Anshuman Singh is saying A and C are correct. Okay, let's see. Okay, next, so let's find this equivalent channel first. Means we have to find this transition probabilities, we have to find out. So you have to get this equivalent channel diagram. So these are p z by x probabilities, this p z by x probabilities, this conditional probabilities we have to get. Okay, so once you get that equivalent channel matrix is also called as conditional probability matrix. So you have to get equivalent conditional probability matrix, equivalent channel matrix you have to get, p z by x you have to get. Okay, yes. So I'm writing here p z by x. See this, how to get this is for what is the probability of transmitted x to be received as z. For transmitted x to be received as z, here first x should be received as y, okay, and y should be received as z. This is okay. So if you see p y by x here, so if you write p y by x here, so first map like this, otherwise you will get confused. So x1 x2 transmitted, y1 y2 received. Okay, what is the probability of transmitted x1 received as y1? Okay, transmitted x1 received as y1 is 0.9. This is, then x1 received as y2 is 0.1, and probability of transmitted x2 received as y1. Okay, x2 received as y1 is 0.1. This is 0.9. This is py by x. Okay, similarly you can write pz by y also you can write. So let me write directly. Now pz by x I'm trying to write. So this is 0.9, 0.1, 0.1 and 0.9. And what about pz by y? So what is the probability of transmitted y1 received as z1? y1 received as z1, okay, that is 0.75. Okay, this is, then it is 0.25, 0.25 and 0.75. So if you see matrix multiplication, you know matrix multiplication, multiply these row elements with this column elements. So if you do that, you will come to know this is 0.7, 0.3, 0.3 and 0.7. This is, yes, you can map like this. This is x1, x2 transmitted and z1, z2 received. So what is that corresponding channel diagram will be? Okay, x1, x2 transmitted and z1, z2 received. So this is the equivalent channel I'm writing. Okay, yes, transmitted x1 received as z1, that is 0.7 and this is 0.3, and x2 received as z1, this is 0.3 and 0.7. So this equivalent channel is also binary symmetric channel. This is, so 0.3 and 0.3 equal. So this is also binary symmetric channel. And the capacity of this equivalent channel is denoted with C. Okay, that will be 1 plus this is 0.3 log 0.3 base 2 plus 0.7 log 0.7 base 2. Okay, and if you do this, you will come to know this is 0.1187 bits per symbol you will get. This is okay. Now we got C1, C2 and C also. So what is C1 we got? Let me write once again, 0.531. No? This is, so C1 0.531 we got. Okay, and this is C2 0.188 and the capacity of the equivalent channel 0.118. So here it looks to be okay. C here, what you got? It is less than C1 and less than C2 also. So here, yes, C here less than C1, less than C2. So B is incorrect. And what about relation between C1 and C2? Yes, here C1 greater than C2, no? Yes, C1 is greater than C2. So here this is incorrect. So A and C will be correct. Yeah, that's very good. So Amit and Anshman, okay, very good. Yeah, Barik, correct. A and C are correct. Good. Let's see the next one. This is also interesting. Try this. Yes, let me read this for you. The channel has the following transition matrix. Transition matrix means this is okay, conditional probability matrix only. Okay, means if you see the input is X, the output is Y here. Okay, so this is, you can see as P Y by X matrix only. This P Y by X matrix it is, because sum of the elements of each row 1 here, sum of the elements of each row 1 means it is P Y by X matrix only. Okay, and this conditional probability matrix here is P Y by X matrix, and the channel input probability matrix. Okay, here you can, I'm giving some notations here. So 3 inputs and 3 outputs. That inputs I am denoting with x1, x2, x3. The outputs I am denoting with y1, y2, y3. This is, so the channel input probability matrix. So input probability matrix means Px only. You can understand this is, here is talking about Px matrix. that results in equally likely channel outputs. Equally likely channel outputs means the channel output is nothing but Y only. Okay, so it is PY matrix is given. Equally likely channel outputs means equal probability. Okay, so 3 possible outputs, Y1, Y2, Y3, that too with equal probability, so that is 1/3 each. This is, so PY is also row matrix only. PX and PY both are row matrices only. Okay, and what that PX matrix denoted here is PX1, PX2, PX3. Okay, so what is given here is the input probability matrix is such that, okay, PX1, PX2, PX3 is such that it results in equally likely channel outputs. The PX matrix is such that, okay, it results in equally likely outputs it results in. PY matrix is like this. Then PX1 equals to how much you have to find out. Okay, so here, okay, PY by X matrix is given, PY matrix is given, and this question is about finding PX matrix. PX matrix, that too, okay, it's not about all elements, you have to find only PX1 you have to find out. So what that PX1 value will be. He can ask you what is PX2 or PX3 also. Now here I am asking to find out PX1. Any idea how to get PX elements? So here PY by X is given and PY is given. Okay, PY is given and you have to get PX you have to get. Okay, how to get PX? Any idea? Yes, if you see this, yes, we know that PY is equals to PX into PY by X. It is a relation between these three matrices, PX, PY, PY by X. What is the relation between these three? PY is PX into PY by X. Now we need PX matrix, we need. How to get PX matrix? So to get PX, so both sides multiply with PY by X inverse. So if you multiply both sides with PY by X inverse, so PY by X and PY by X inverse, that is identity matrix, and that results in PX only. Okay, and that PX will be equals to, this is PY into PY by X inverse. This is okay. So PX means don't write directly division. You can't do matrix division directly. Okay. If at all you are dealing with diagonal matrix, okay, then you can do that division. Division of matrices you can do when you are dealing with diagonal matrix. So when you are dividing with diagonal matrix, that can be done. But between normal matrices, you can't do division just like that. That is inverse only. That is. So multiply both sides with PY by X inverse. Okay. Okay. Then PX is equals PY into PY by X inverse. It will be equals to. Okay. Yes. Now it will be. You have to do right side only. You have to do that multiplication. PY by X into PY by X inverse. PY by X into PY by X inverse. Okay. So PY into PY by X inverse. So the inverse matrix you have to get. So PY by X is given, and you have to get inverse matrix to that. Inverse to that. I think in mathematics you studied how to find inverse. Okay. So I'm taking PY by X is some PA matrix for my convenience. Okay. So this I'm writing. This is PY into this is, so it is some matrix A I am taking. This is PY by X is some A, so A inverse. So I'm taking this is some matrix A, this is, and inverse of this you have to find out. Okay, so this A inverse will be equals to, this is, how to find A inverse? So adjacent of A by determination of A. Vinish Modi is saying Px in diagonal form into Py by x. No, that's incorrect. So Vinish Modi, you are saying Px diagonal into Py by x. But how you, this is the question, you have to get Px, you have to get, that is the question. So if you multiply Px diagonal, Vinish, if you multiply Px diagonal with Py by x, you will get Px comma y matrix, you will get. Okay, but here the question is, you have to find that Px diagonal, you have to get. Px elements, how you will get, that is the question actually, finding Px elements. Okay, now if you see, so let me write this matrix A here, this is, so that is given as 0.5, 0.3, this is 0.2, Anshman saying 8 by 15, okay. Let's check, okay, and this, then 0.2, 0.6, 0.2, this is, next 0.1, 0.2, 0.7, this is, it is Py by x, I am denoting with A. So if you see, what is the determinant of A? I think you know how to find determinant of a matrix. Okay, this is, if you see 0.5 into, this is 0.5 into, so this is 0.6 times 2, 0.7, this is 0.42 minus 0.04 minus 0.3 times 2, this is 0.14 minus 0.02 and plus 0.2, this is 0.04 minus 0.06. Okay, what is the determinant of A you will get is, okay, so this is 0.15 you will get. Okay, so how to get adjoint of A? So to get adjoint of A, so many shortcuts will be there. Let me use one shortcut. Okay, this is, it will be, first write these elements as it is. Okay, this is 0.5, 0.3, 0.2, this is, next 0.6, 0.2, next 0.1, 0.2 and 0.7. Okay, so next repeat the first two columns again. This is 0.5, 0.2, 0.1. Second column also do repetition, 0.3, 0.6, 0.2. Okay. So repeat the first two columns again. Next repeat the first two rows here, this first two rows, that is 0.5, this is first row, this is, so repeat this first row and repeat this and the continue this repetition, 0.5, 0.3, 0.2, again 0.5, 0.3, this is, yes. The first row do the repetition, the second row also, this is 0.2, 0.6, 0.2, 0.2 and 0.6. Okay, this is the first just map the A elements like this. What are the elements? Okay, just repeat these first two columns. After repetition of first two columns, repeat the first two rows like this. Repeat the first two rows. Okay, fine. Now neglect this and this. Yes. Okay, then adjoint of A will be equals to, this is, so 0.4 to minus 0.04, this is 0.38, this is this minus this. Next, do this minus this, 0.04 minus 0.21. Okay, this is, so this is 0.17 now, this is minus 0.17, minus 0.17, right in a row. So do this operations AD minus BC, this operation do column wise, but that elements what you will get write in the row manner, you have to write in a row. Okay, next this is this minus this, so 6 minus 12, that is 6 only. Okay, minus 0.06. Okay, yes. Similarly, do for this, this is AD minus BC, this is, so 2 minus 14, this is 12, this is minus 0.12, this is, next 35 minus 2, 33, this is 0.33, this is, next this minus this, so 4 minus 10, this will be 6, minus 0.06. Next, do the operation column wise, but you have to write the elements row wise. Okay, then this minus this, 4 minus 6 will be 2, so this is minus 0.02. Next, so 3 minus of A. Next, then Py by X inverse. And this is A inverse, I denoted this with A is equals to adjoint A by determinant of A. What is the determinant of A you got? 0.15. Okay, and into this adjoint of A. So you have to divide each of these elements by 0.15, you have to divide, then you are going to get this is, yes, it will be equals to, this is 2 point, I'm writing directly, do check this, 2.5333, this is minus 1.1333, this is minus 0.4, this is minus 0.8, and this is 2.2 you will get, and minus 0.4, and this is minus 0.1333, so this is minus 0.4, this is 667, and this is 1.6. This is Py by X inverse. Then Px is equals to, yes, Py is what? 1 by 3 each, okay, into this Py by X inverse, this Py by X inverse. Okay, and you know matrix multiplication, no? This is, so multiply this row elements with this first column elements, and multiply this row elements with second column elements, multiply with third column elements, and if you do that, you will come to know Px will be equals to, this is, so this is 0.5333, this is 0.2, and this is 0.2667 you will get. Do the matrix multiplication, multiply this matrix with this matrix, okay, Py into Py by X inverse. Okay, then if you can check this, okay, the total sum of elements of course will be equals to 1. Okay, because px1 plus px2 plus px3 of course will be equals to 1. And here the question is about finding px1 only. So px1 is equals to 0.5333. This is okay. So 0.5333 will be the answer. This is 0.5. Yes, Abhinav, that's the correct answer. So even if you give the answer in examination point of view, okay, even if you give the answer 0.53, that will be correct only, 0.53 or 0.54 or 0.52. So they will give some range, some specific range of inputs from your side, okay. So they will give the marks for you, okay. So in examination they will give the range such that even if you give the answer 0.53, okay, or 54 or 52, so you will get the correct, you will get the marks, okay. Fine. Next question. So next question, I give an easy question. Try this. So for a LBC, linear block code, so G is the generator matrix, H is the parity check matrix, C is a valid code word. Okay. So LBC will have so many of valid code words in it, and one of that valid code word is denoted with C. Then which of the following is or are correct? So it is also MSQ type question. So here one or more options will be correct. So tell me which options will be correct. The Damodar correct. 0.53 is correct. Very good. This is easy one. I'm expecting answers from you. Yes, it will be. Yes, some standard results we know, that is for post your answers in the comment box. I'm looking for the answers from you. I'm waiting for answers from you. So hello Bhattacharya, okay. I think you're all my students only, na? Samskriti Gautam. I can recollect your names, okay. Good, happy to see you, Yash. Now see this. Yes, we know some standard results, that is for an LBC, okay, G into H transpose will be 0. Yes, G into H transpose of course will be 0. This is a standard result. And C into H transpose also 0. C into H transpose. You know? C. So C is equals to, you can write DG. All these are matrices only. This is D is the data block or message block, and multiplied with the generator matrix. C is equal to DG, okay, and H transpose. So G into H transpose is 0, so this is also 0. So for a valid code word, C into H transpose will be 0. And of course G into H transpose is 0. Okay, so here you can see this. So G into H transpose 0 and C into H transpose 0. C into G transpose 0, it is incorrect. And H into G transpose, actually this is also correct. Okay, just simple, okay. Simple analogy of matrices. Okay, so if you apply inverse on both sides, so if you apply inverse on both sides, what it will be equals to? So this is H into G transpose. If you do the inverse of this, H transpose inverse is H multiplied with the inverse of G is I'm applying transpose on both sides. Yeah. So apply transpose on both sides. Okay. So 0 transpose will be 0 only. That's fine. Okay. And if you apply transpose to this, H transpose, what is the transpose of H transpose is H only multiplied with what is the transpose of G? G transpose will be 0. 0 transpose will be 0 only. Okay. So if G into H transpose 0, then H into G transpose also 0. Just apply transpose on both sides. So H into G transpose also 0. Okay. So your A, B, D will be correct. So most of you given A and D. Okay. Sai Kiran. Yeah. Happy to see you, Sai Kiran. Okay. A and D is given correct, but actually B also will be correct only. Okay, tricky question. Okay. So be careful in examination. Okay, some simple tricks, based on some simple tricks also you can expect questions in examination. So if you see the next question, yes. For a continuous random variable, CRV means continuous random variable, the density function is given fx of x, 1 by 3 root 2 pi e power minus x minus 4 squared by 18. Find differential entropy of x. So this question is about finding differential entropy, okay, of the given random variable. So this is of course Gaussian random variable, you can understand. Okay, it is a Gaussian density function. So if you see differential, yeah. So let me give you one standard result. If you see standard Gaussian density function, okay, so this is 1 by under root of 2 pi sigma square into e power minus x minus a square by 2 sigma square. Okay, so it is the, here x is a Gaussian random variable whose mean is a, okay, and variance is sigma square. This is the density function. And if you see the differential entropy of this Gaussian random variable x, what is the formula will be integration minus integration, okay, fx of x, this is log fx of x dx, and base will be of course to 2. Okay, fx of x log fx of x. And if you don't want to write minus here, this is fx of x log 1 by fx of x dx. Yes, the entropy of a continuous random variable is called as differential entropy. So it is the differential entropy of a continuous random variable. This is the formula. And if you substitute fx of x here, okay, this Gaussian density function fx of x, if you substitute and do simplify this, then it is going to be like this. It is like a standard result, half log 2 pi e sigma square, this is base 2. Okay, so this is, if the random variable x is n of a comma sigma square, in compact form you can write like this: x is having normal density function or Gaussian density function with mean a and variance sigma square, then what is the differential entropy of that random variable? Half log 2 pi e sigma square. Remember it as a formula. Anshuman is saying 3.63. Very good, Anshuman. I'm happy with your result. I'm happy with your answer. I think 3.63 will be the correct answer. Yes, here. So from comparison, if you compare this with the standard Gaussian density function, this is a will be equals to 4 and sigma square is equals to 9. Okay, and if you substitute now, if you substitute here, so remember it as a formula, everyone. Okay, will be useful to you in examination. Then hx will be equals to half log base 2, this is 2 pi e sigma square, this is sigma square is 9, okay, 9, if you substitute 9, this is 18 pi e, this is base 2. So this is, you will get 3.63, you will get. 3.63. So here option C is going to be correct. So see the next question. Yes. You see this, a computer is generating binary words, fine, each consisting of 16 bits at a rate of 1500 words per second. Okay, so each binary word okay, each of the binary word consisting of 16 bits. Okay, each binary word is having 16 bits, and the computer is generating 1500 words per second. Then how many bits generated in 1 second from the given computer? How many bits generated in 1 second? So one word contains 16 bits here. So this is 1500 into 16. This is bits per second. So this is the bit rate of the source. I'm denoting with RB. Okay, and if you do that, it comes to be, try with calcium. So this is 24,000 bits per second. RB is equals to, this is BPS, bits per second. Okay, then what you have to find out is, you have to find the minimum M such that this output, okay, this binary data can be transmitted as an M-ary PAM signal. So this question is about M-ary PAM. Okay, on a channel whose bandwidth is limited to 30 kilohertz is how much? So you have to find what is the minimum M value required for M-ary PAM, M-ary PAM. So this binary data is transmitted by using M-ary PAM. Okay, and where the channel bandwidth available is 30 kilohertz, then what is the minimum M value required for, okay, satisfactory transmission? What is the minimum M value required? We have to find out. Okay, so for satisfactory transmission, I can say channel bandwidth should be greater than or equal signal bandwidth. What is the channel bandwidth available is given is 30 kilohertz. 30 kilohertz. Okay, greater than or equals to. Okay. The signal bandwidth. Okay. The default we take that minimum bandwidth only. Okay. That is, what is the minimum bandwidth is in transmission of binary sequence through baseband channel. Okay, so by using PAM, okay, you can expect baseband transmission only. So in baseband transmission, the minimum bandwidth will be equal to RB by 2, but this is given as M-ary PAM. M-ary PAM means this is RB by 2 log M base 2. So that can be M-ary PCM or M-ary PAM. That minimum bandwidth will be RB by 2 log M base 2. Okay, so this is 30,000. This is greater than or equals to RB. RB is equals to 24,000 by 2. This is log M base 2. This is. So it comes to be, yes. So log M base 2 greater than or equals 4, you will get this is M greater than or equals 2 power 4. So M greater than or equals 16. So M minimum equals to 16. So everyone is giving the answer is 4, okay, but that is 16, okay. m value you have to find out. Will be 16 you will get. (24) This is, it's 240k actually. This is, it's not, this is, yeah, bits per second. 240k this is actually, this is, you'll get one more zero. This is, so 30,008 are this much, and 2 4s are 2 4s are 8. So log 4 to greater than or equals 4. Yes. So the next question. Let's do this. It's a good question. Yes, a signal. Let me enlarge this. I'm not doing questions on map and ML decoding because so if you see the last couple of years, every year, okay, they given questions on map and ML decoding. Okay, so that's what I'm not going for this, because so many questions, so many model of questions already given in GATE examination. So I want to cover the questions on other topics. Okay, yes. Here, a signal has a Gaussian amplitude density function, okay, with 0 mean and variance sigma square. Okay, so here the signal given is a random signal, you can understand. Okay, and that random signal, if you see the amplitude density function of that random signal, so that is Gaussian with 0 mean and variance sigma square. So that signal I'm taking x, that random signal I'm taking x here. Okay, and this is 0 mean and variance sigma square. The signal is sampled at 500 samples per second. This random signal is sampled at 500 samples per second. Fine. And this samples, and if you see the density function of x here, this is. So if you say a random signal, any random signal, some x of t, okay, if you see its amplitude, that amplitude of random signal, okay, is following a Gaussian density function with 0 mean and variance sigma square. And that amplitude of random signal, okay, I'm denoting with x, okay, and this is following Gaussian density function. And if you see this, 1 by root 2 pi sigma square e power minus x square by 2 sigma square. And if you plot this, this is fx of x with respect to x. So it is maximum at x equals 0. So this is going to be like this. Yes, it is the density function of x. Okay, so the amplitude of this random signal can be any of this, from minus infinite to infinity, and with this respect to probabilities. So from this density function you can get the probabilities. The area under density function will give you corresponding probabilities. Yes, and this random signal is sampled at 500 samples per second. Fine. And these samples are quantized according to following table. So the quantization is done according to this table, the quantizer input and quantizer output. Okay, so if the x value, if the sampled value in between minus infinity and minus 2 sigma, that is quantized to m naught. Okay, and here is denoting some values like this. Here this is, so minus 2 sigma, some values like minus 2 sigma, this is minus sigma and sigma, and this is 2 sigma like this. Okay, Means if x value in between minus infinity and minus 2 sigma, okay, means if you see the amplitude of this random signal, that amplitude of random signal can be any value between minus infinity and infinite. So if that x value in between minus infinity and minus 2 sigma, that is quantize it to m naught, and if that x value in between minus 2 sigma and minus sigma, that is quantize it to m1, like this. Okay, now what we have to find is entropy at quantizer output. We have to find out what is the entropy at quantizer output. So what we get at the quantizer output, we get this quantized values. We get these are the quantized values, okay, and these quantized voltages, quantization voltages, we expect at the output of quantizer, and we have to find entropy at this quantizer output. Okay, the entropy is bits per sample. Okay, fine. Here quantization is done for the samples. Here the samples are getting quantized. Okay, so the samples are getting quantized. Okay, then actually if you are doing, okay, if you're finding if you do for coding of symbols, okay, then units of entropy will be bits per symbol, and if you're doing coding of samples, the units of entropy you can write bits per sample. You can write here q1, q2 values are given here. Okay, so you can take the values, you can take the help of these values. Okay, fine. So here what you can understand is, yes, here the quantization is done based on okay, so here the encoding will be done based on the probabilities. You can understand here. So first quantization is done, and this quantization voltages will be encoded based on the probabilities. Okay, like here the coding what he is doing is source coding, like, okay, the coding will be done based on the Shannon-Finer coding or Huffman coding. The coding will be done based on the probabilities. That is called as source coding. Okay, so first we have to find the probabilities for this quantization voltages. Once you got the probabilities, you can find the entropy. So to find the entropy, we need the corresponding probabilities. Means what is PM0, PM1, PM2, like we have to find. Means at the output of quantizer, okay, to get M0 at the output of quantizer, what is the probability? To get M1 at the output of quantizer, what is the probability? We have to get those probabilities. Once you got those probabilities, you can find entropy, and here based on those probabilities the coding will be done. Here is what you can understand. Okay, yes. Now here first let me find, this is okay, PM2, okay, PM3 I'm going to find out. Okay, means what is the probability to get M3 in the output? To get M3 in the output, x value should be in between 0 and sigma. Okay, if your x value is in between 0 and sigma, okay, then okay, those samples will be quantized to M3. The samples will be quantized to M3. So what is the probability of M3 in the output? Is nothing but what is the probability of x is in between 0 and sigma. This is, if x value in between 0 and sigma, okay, then that is quantized to M3. So what is the probability of M3 at the output of quantizer? Is nothing but, okay, what is the probability of x is in between 0 and sigma. Okay, and one thing you can understand, okay, the probability of x to be in between 0 and sigma and x to be in between minus sigma and 0 will be same. The Gaussian density function symmetrical about its mean. Okay, so what is the area from 0 to sigma, and area from minus sigma to 0 will be same. So x to be in between 0 and sigma, and minus sigma and 0 will be same. Minus sigma and 0 will be same. So this PM2 will be same as PM3 only. This is, so it is same as PM2. Okay, yes, and it will be equals to integration 0 to sigma. How to get probability from density function? Area. So 0 to sigma, this is fx of x dx. It will be, okay, let me find this. So this is integration 0 to sigma. Fx of x is given 1 by root 2 pi sigma square. If you write sigma square outside to this under root, that is sigma e power minus sigma square by, this is 2 sigma square dx. This is the Gaussian density function given. So to get the value of this, okay, here the q value is given here, so take the help of q function. Okay, so to write this in terms of q function, So you know the definition of q function, no? Qx is equals to, this is 1 by root 2 pi, this is integration x to infinite e power minus y square by 2 dy. Okay, that will be equals to qx. Okay, so to write this in terms of q function, okay, I'm assuming let, okay, y is equals to, this is x by sigma, this is, then it will be in the form of e power minus y square by 2, same like q function you will get. Okay, y is equal to x by sigma, then dx is equals to sigma dy, then it will be, then how the limits will be changed. If x is 0, okay, y is also 0, fine. If x is sigma, y will be 1, okay, and this is 1 by, of course, root 2 pi sigma into e power minus y square by 2, dx is sigma dy, and here the sigma sigma will be cancelled. Okay, then it will be equals to, this is integration 0 to 1, yes, let me write 1 by root 2 pi, I'm writing outside, and it is integration 0 to 1 e power minus y square by 2 dy. How to write this in terms of q function? Okay, you can do normal integration for this, or you can write this in terms of q function also. How to write in terms of q function? This is, so this is q0 minus q1. Okay, yes, yes, if you see the area 1 by root 2 pi e power minus y square by 2, okay, this is the Gaussian density function only. If you see, this is 1 by root 2 pi e power minus y square by 2, this is with respect to y, this is 1 by root 2 pi e power minus y square by 2, I plot it. And if you find the area under this from, okay, how to understand q function is, the area under this Gaussian density function 1 by root 2 pi e power minus y square by 2 from x to infinite. So if you see some x here, x to infinite, so will be equals to qx. This area you can see as qx. Okay, but here we have to find area under this Gaussian density function, okay, from 0 to 1. The area, you have to find the area from 0 to 1. This area you have to find out. You have to find this area 0 to 1. Okay, this is simply, you can write q0 minus q1, you can write. q0 means area from 0 to infinite. So from that, if you subtract area from 1 to infinite, you will get area from 0 to 1. So you can write q0 minus q1, you can write. Okay, so this is, so you can write this as q0 minus q1. q0 will be how much? 1 by 2 now. q0 is 0.5. Area from 0 to infinite, this is actually, yeah, so this is 0 to 1. So 0 is here only, no? This is, so this area you have to find out. Area from 0 to 1. So this is q0 minus q1, you can write. q0 means area from 0 to infinite. From that, if you subtract area from 1 to infinite, okay, you will get area from 0 to 1. q0 is of course 1 by 2, area from 0 to infinite. Okay, okay, that will be 1 by 2. So 0.5 minus q1. q1 is given how much? Yes. Yes, what is q1 given in the question? 0.1587. This is, so 0.1587. This is, so this will be, yes, this is 0.3413. This is 0.3413 you will get. Next, so PM3 and PM2 you got. Yes, no? PM3 and PM2. Then let's find this. Okay, PM4 and PM1 you will get same. Okay, So the area from sigma to 2 sigma and minus 2 sigma to minus sigma will be same. Minus 2 sigma to minus sigma, the area will be same as sigma to 2 sigma. So this PM1 and PM4 you will get same. So this is PM4 will be equals to, this is, okay, what is the probability to get M4 in the output? Okay, to get M4 in the output, okay, at the output of quantizer, X should be in between sigma and 2 sigma. This is, if X is in between sigma and 2 sigma, then okay, those samples will be quantized to M4. Okay, so to get M4 at the output of quantizer, X should be in between sigma and 2 sigma. So this PM4 will be same as PM2. Okay, and this will be, it is integration sigma to 2 sigma. This is fx of x, 1 by under root of 2 pi sigma e power minus x square by 2 sigma square dx. So if you write in terms of q function, so the same thing, let y is equals to x by sigma, and do the simplification, then you will come to know if x is sigma, y is equals to 1, and if x is 2 sigma, y will be 2. Okay, and this is, you will get 1 by, do simplify it, then you will get 1 by root 2 pi e power minus y square by 2 dy. Here sigma sigma will be cancelled. How to write this in terms of q functions? This is q1 minus q2. This is, so if you substitute q1 minus q2, q1 q2 given in the question, I know this is q1 and q2 values given in the question, will be given to you in the question. Okay, and by substituting that q1 and q2 values, it will be equals to, this is 0.1359. This is 0.1359. Next, I'm finding P. Similarly, this is, yes, this PM5 and PM0 will be same. Okay, what is the area from 2 sigma to infinite and minus infinite to minus 2 sigma will be same. Yes, no? The area from minus infinite to minus 2 sigma to infinite will be same. So PM5 equals to, this is PM5. It is, what is the probability of X is in between 2 sigma and infinite? This is 2 sigma to infinite, 1 by under root of 2 pi sigma into e power minus x square by 2 sigma square dx. Okay, then if you simplify this, this will be equals to, this is, you will get in the form of 1 by root 2 pi, okay, integration 2 to infinite, you will get the similarly same, assume y is equal to x by sigma, then you will get like this, e power minus y square by 2 dy. It is simply area from 2 to infinite, means simply this is q2 you can write. The area from x to infinite is qx, area from 2 to infinite is q2. So what that q2 value given, 0.0228 now, this is 0.0228, that is q2 is given. So this PM5 is same as PM0. Then we have to find entropy at the output of quantizer. Okay. Yes, here the x is the input to the quantizer here, q means quantizer, and at the output of quantizer you will get the quantization voltages M0, M1 up to M5, you will get quantization voltages. Depending upon the x value, the quantizer output can be any of this. Okay, and you have to get the entropy at the quantizer output, H is equals to, yes, to get the entropy we need probabilities, so that is minus summation I is equals to 0 to 5, this is PMI, this is log PMI base 2, this is, okay, And if you do this, okay, if you do substitute these things, yes, this is here Pm naught log Pm naught will be same as Pm phi log Pm phi. Okay, that is repetition only. So 2 times you will get. So this is minus 2 times 2. This is so 0.3413 log 0.3413 plus. Okay, and the other probability is what you got, 0.3413 and 0.1359 you got, and log 0.1359 base 2 plus this is 0.0228 log 0.0228. Okay, and if you do this, it comes to be 2.09 bits per sample you will get. This is the entropy at the quantizer output. It's not 2.09. This is, so it is NAT, numerical answer type question. So 2.09 will be the correct answer. So let me just extend this question. If you want to find information rate here, if he is asking information rate, so once quantizing is done, okay, this quantization voltages will be encoded, and after that encoding, what the information rate or bit rate you will get is how many bits will be generated in 1 second. Information rate or bit rate. Okay, I'm denoting with capital R. So this is bits per second. Okay, bits per second. So here the encoding will be done based on the probabilities. Here we already got the probabilities Pm0, Pm1, Pm2, the probabilities we got, and based on those probabilities encoding will be done. Like by using Shannon-Fano or Huffman coding, okay, that coding will be done. Okay, source coding will be done here. Okay, and in that coding process, how many bits generated in 1 second? This is bits per, this is sample into sample per second you can write. How many samples generated in 1 second, and each sample represented by how many bits. So bits per sample is entropy only. This is actually in the source coding process. So it's a good question. So take care of this question. What we just done is a good question. So if you see the next question, I will close with this question. Okay. So we already took this session for almost 3 hours. Okay. Now, so this is a simple question. So which of the following is or are valid ACF, valid autocorrelation function? Okay. Yes. So if you see this is also MSQ type question, multiple select type question. So one or more options can be correct here. Okay. Now, so this is the ACF given. Okay. So ACF, one basic property is it should be even function. R of minus tau is R of tau. So it is even function of course. Okay. And even if you see the PST, the Fourier transformation of ACF will give you PST. So what is the PST here? What is the Fourier transformation of this? A by 2 del f plus f naught plus del f minus f naught. So it is of course valid ACF. Okay. Valid PST, this is valid PST, because PST also should be even function. Of course it is even function, and the valid PST always will takes positive values only, never takes negative values. So it is valid PSD, correspondingly this is valid ACF. The second one is, so A, it is triangular function. Okay, this is, it can be given like this also. It's a triangular function. This is, so if you plot this, this is, so it is, if you plot this, the height will be A, okay, and this is, so tau by, this is with respect to tau axis, tau by tau naught means minus tau naught to tau naught. This is, yes, this is even function, you can see. It is even function, the first condition is satisfied. Okay, and one more thing is, so if you see PST for this, if you see the Fourier transformation of this, what is the Fourier transformation of this? It is, I think you know this, it is standard result. A tau naught, this is sinc square f tau naught. This is the Fourier transformation. This is PST. The Fourier transformation of ACF will give you PST. Okay, so this PST, you can see this is also taking only positive values. Sinc square taking only positive values, and this is also even function. PST is also even function. So this is valid PST. So this is also valid ACF, I can say. And if you plot this, this is, if you plot this rectangular function, this is pi or rect can be given, and the height is A here, this is, and this is minus tau naught, this is, yeah, this tau naught specifies width. So this is minus tau naught by 2 to tau naught by 2 with respect to tau naught. Okay, and if you see the Fourier transformation to this, it is even function. This is even function, that's okay, fine. ACF should be even function, this is even function. And one more thing, let me check this. So if you see PST for this, the Fourier transformation of this will give you PST. So that is A tau naught, this is sinc f tau naught, this is, okay. So if you plot the sinc function, okay, the sinc function, sinc will takes negative values also like this. If you plot the sinc function with respect to f, it is taking negative values. Okay, so it is not valid PST. Okay, valid PST should take only positive values, but it is taking negative values also. It's not valid PST, so I can say it's not valid ACF. It's not valid ACF. Okay. Okay, yeah, so it is one better way to check whether the given is valid ACF or not. Okay, so the PST is not valid PST, so this is not valid ACF, and this is of course not valid ACF because it is itself not an even function, so it is not a valid ACF directly, you can see. Even it is even function, so check for PST once, okay, and if that is valid PST, then you can say that is valid ACF. So it is not valid ACF, so I can say A and B will be correct here. Okay, A and B will be valid ACF here. A and B will be. Okay, fine. Okay, we are running out of time, so I almost spent 3 hours, more than 3 hours. So I'm closing this. Okay, I hope you got some good questions here. So thanks for your time, and I hope these questions, okay, will help you in the coming GATE examination. So I hope for that. Okay, so in the examination, don't be so hurry at the time of examination. Okay, try to get the answers step by step. Okay, try to do the questions step by step. Okay, don't be hurry. And in examination, try to do easy questions first. So once you get the answers to that easy questions, you will get the enough confidence to try for the typical questions. Okay, in that way you can proceed. So I hope you will do good in the examination. Okay, I will hope for that. I will pray for that. Okay, so thank you very much, guys. All the very best. Thank you.